Now the recorder is on, and let's get started. So did you guys enjoy the weekend without any cisp310 homework? Okay, so now we have a homework again. We have a homework assignment. So we'll talk about the homework assignment, and I'll give you guys the concepts that you need to do the homework assignment today. So by the end of today's lecture, you should have everything that you need in order to get started with that homework assignment. All right? So let's go ahead and get started with that first. And for those of you who use my distribution, I suspect that no one in this class actually does that. I have a new distribution, and apparently it works better than the previous one. So
yeah, if you're interested.
Sorry?
I tried to get yours running, but I couldn't actually do this work.
Okay. Did it even boot or not?
No, I couldn't install it.
You could not install it? You mean the ISO?
Yeah, ISO.
So the ISO would not start from a USB drive?
Yeah, it wouldn't actually.
Okay, so the way you install it onto a USB drive, you have to use DD to overwrite the entire drive and not to put it as a file. It wouldn't start up. Oh.
Okay. Just so you know.
Okay.
Yeah, I did the same thing, and I'm running Debian.
No,
so
I actually put it.
you would think it was going to work for anything, but no.
It has to do with your BIOS, how it starts up.
Yeah.
If you have UEFI, it doesn't work. This one does not.
This is an old machine. It has BIOS, not UEFI.
Okay. All right.
Calling it now Legacy.
Legacy. Oh yeah. All right. So we are now in topic 6. We talked about the concept of interrupt and how it relates to requesting a service from the operating system. Because the way we surface a hardware interrupt is you can potentially be running in a user program when a hardware event happens. Okay, let's say your Ethernet card has a buffer filled up and it wants the operating system to do something about it. So it will cause an interrupt. An interrupt is a hardware mechanism that is basically saying, hey, operating system, I need some attention here. My buffer is full. You have to get the console and do some processing. Okay. And the mechanism to surface a hardware interrupt is it has to elevate the privilege level of the system first. Because when the system is running an end user application or process, it will be running at a fairly low privilege level so that an end user program cannot corrupt the hard drive, they cannot corrupt memory that belongs to another process and stuff like that. But when you're running the interrupt surface routine, which is the code that you need to run in order to handle a hardware interrupt, it needs to have the privilege level elevated because it needs access to the I/O register, it needs access to RAM, it needs access to a lot of kernel resources. But the problem is, what happens after the ISR is done? What happens after the interrupt surface routine is all done? It has to return control back to the user program that the interrupt interrupted to begin with. So in that process of returning the control, the system, or more like the hardware, will have to return the privilege level back to the previous level, which is lower. Okay, so we talked about this last Thursday, which is basically the elevation of privilege level. Do some code and then drop it back down to the original level when you are resuming execution from where it was interrupted. And that turned out to be the same thing that we want to do when you are requesting the operating system to do something. Okay? Because when you request the operating system to do something, when the operating system is doing it, it requires elevated privilege levels. But when it's all done and it wants to return control back to you, it needs to drop it back down to whatever your program is using. Okay, so it's the same mechanism. So that's why, in this particular slide here, it was, particularly, I guess, we have to turn off full screen mode to get this part. So that's basically, what we were talking about, when we talked about this slide here, in terms of privileges and system calls. So now we are in topic 5, or section 5 of this particular slide, which talks about system call is a request of system service and so on. And the most important part, you can read the rest of it, which is actually what you're supposed to do. But the most important part is here. Each operating system can choose to handle system calls differently. In the case of 32-bit Linux using the i386 processor, it is using the software interrupt vector 0x80, which is 128 in decimal, in order to get it. This is the universal entry point to request Linux, the Linux kernel, to do something. Okay, so whether you want to read file, you want to read from a file, you want to write to a file, you want to start up a new process, it is still the same location. It is using interrupt vector 80 in hexadecimal. Okay. Are there any questions about what I just talked about on last Thursday and also up to right now today? No questions? Okay, when I show you the code, it becomes a lot more clear of what to do or what this is all about. Okay, the next paragraph, okay, I think this is pretty hard to read because it's too wide, so I'm going to change it so that it's easier to read. In order to differentiate which surface is actually requested, what we need to do is to set up EAX as a number to say that I want to use system surface number 1, I want to use system surface number 2, and so on. So each number that you put into EAX, acts as an ID to basically identify, okay, what do you want me to do? It's the kernel asking, okay, what do you want me to do? And you use the value in EAX to specify what you are actually requesting the kernel to do. Okay, moving on. In order to read a file, EAX should have a value of 3. That's basically, it's kind of hard-coded. 3 is the identifier of reading a file. 4 is writing to a file. 1 is for exiting a process, and so on. Are there any questions about this part of the discussion? EAX is an ID for what you're requesting. EBX, is one of the quote-unquote parameters, and so is ECX and EDX. So the other registers can be used as parameters to basically say, okay, I can see that you want to read a file, but which file are you reading from? How many characters do you want to read? And where do you want me to put those characters once I'm done reading those characters from the file? Okay, so those are specified by EBX, ECX, and EDX in the case of system surface number 3. Okay. Are there any questions about the general mechanism of requesting the operating system to do something for you? In this case, it's reading content from the file. Questions? Now I can actually give you a sample program to illustrate all of these things. So let's go up one level. In this class, we are not going to talk about signals, so don't worry about section 6 and beyond. Okay, all of those concepts really do not apply to this particular class. Is anyone interested in why do I write about signals, handling signals, and so on and so forth? It's not for cisp310, it's for cisp 453 Linux system program. Okay, because in that class, you do have to kind of understand what a signal is and how to deal with signals using a handler. Yep.
I was just wondering when is that class offered?
Whenever we can convince the department chairs, because there are 2 co-chairs, that we have enough interests to start up that class again. Because right now we are not offering it because in the past, for the past few years, it's really hard to get enough students to get that class started. But I think at this point, we are tipping over, and basically saying if we offer that once a year, we'll probably have enough students. The problem with CISP 453 is it only transfers to certain colleges or universities like Sac State, but it does not transfer to any of the UCs. So that's why we lose like 1/2 or more than 1/2 of students in a typical class like this one, and that's why that class usually does not fill up. Is that answering the question?
Yeah.
Okay, so that's basically the reason why we don't offer that class much or anymore. Yep.
So do they accept petitions to make that happen?
I think you can talk to Damon personally, and
Group letter to the dean.
or talk to the dean. The dean is the one ultimately with the authority to say, okay, we have to offer that class again.
Yeah.
And if there are like 22 plus students sending an email in this one semester saying that we need that class because I want that class to go to Sac State or another university, I think that would be enough proof that there's enough interest, right? Well, 22 unique students. Okay, you cannot be the same student with 22 Gmail accounts, right?
No, it's nice to go around.
So you might want to send it from your W followed by 7-digit at apps.losrios.edu account, just so that it is legitimate. Okay, this is one student, this is another student, and so on. If you send it from some student at gmail.com, that may not work well. Some student 1, some student 2, some student 3. They count it all up to just 22, right? Because we just need 22 to start a class. All right. But that was a fun class to teach. I talked about multi-threading, multi-processing, socket programming, which is really, really fun in that class. The difficulty of that class is to adjust the difficulty level of quizzes and tests. Okay, this is also interesting. This is very useful for this class also. It's a call table, okay? It talks about what value you can put into EAX and what surface it is actually corresponding to. So 1 is corresponding to exit, 2 corresponds to fork, which is how you start up a new process in a Unix type operating system. 3, we talked about already, it is a read operation. 4 is a write operation. 5 is an open operation, which means you're telling the system, this is the name of the file, and I want to open it. Okay, and then the system will give you what we call a handle, which is just an integer, and say that from now on, this file is associated with this number. We have closed, basically saying that we are done with accessing this file. We're closing the file. Wait PID, waiting for a process ID in this case. Create, which creates a file. Link, unlink. Unlink, by the way, is actually delete. Okay, this is how you can delete a file in the system. Change directory, time, make end node, make node, chmod, change. Chmod is change modifier. Okay, so it changes the permission flags of a file, and so on. So all of these, are basically primitives to the Linux kernel, and that's basically what the kernel can do for any application program, okay? Including Bash. What is Bash? B-A-S-H. What does it stand for? Other
Born
than
again shell. Born again shell.
Born again shell, exactly. So it is a shell, but what exactly is a shell program? How does a shell like Bash or C shell relate to an operating system like Linux? What happens?
The kernel.
Sorry?
Makes calls to the kernel.
It makes it interactive. Okay? So Linux by itself does not require Bash, it does not require C shell, because the kernel is really just a kernel. If you have an application program that can run and directly contact the kernel, using these system services, you don't need shell. You don't need a shell to interact with. So what a shell is really a way for you to interact with the operating system. So you can say, oh, by the way, I want to move this file from here to here. I want to create a subfolder here. I want to delete a file over here, and so on. So a shell is more or less, an interactive mechanism, so that an end user can use a keyboard and a screen, the console, to interact with the kernel of the file of the operating system. But it is not an essential component. For any system that is non-interactive, you can uninstall Bash and it will still work just fine. Okay? Although it does make it kind of difficult to do administration on that computer without a shell. All right, so moving on. So you can see that this list, gets pretty long. If I just kind of go all the way down, there are 190. The numbers are not contiguous. Type of things or type of requests that you can place on the operating system. Now, how do we read all these things? Well, as it turns out, exit is an item that you can look up by using the man pages. Same thing with fork, read, write. Those are things that you can actually look up using the man command for manual. So let me go ahead and demonstrate how you can look it up. So in this case, I open up a new tab and just say man, which stands for manual. And we just say, 2, which means, section 2 of the man pages, and read. And that pops up this particular man page, which is basically a help file. And it shows you something that is consistent with what we are seeing here on the with the web page. Let me just scroll a little bit and see if I can display both at the same time. So I want to display read all the way to the top here, and then show the screen here. Okay, so read in this case, has 3 parameters. The first parameter is an unsigned int, and unsigned int, which is the file descriptor. The second one is a character pointer here, which is represented as a void pointer here. It is the buffer. And the last one is the size of, or the number of bytes to transfer, which is translating to count over here. In other words, if you read, if you want to look up a particular system call, you can look up this table and find out what is the symbolic name of that system service, and then use the man pages to find out, what does it mean when I pass this parameter to, this particular call. Are we doing okay so far, with reading that table that gives you the number of the system services, the symbolic name, and then use that to look up the man pages in order to find out, okay, what does it mean? What is the first parameter doing? What is the second parameter doing? And so on. Any questions? We will talk about read and write in more details. I just want to give you the resources if you want to read it by yourself and understand, better what it does. This is how you look up the information. Right? Okay, so so what we want to do is to say, okay, now that we know this kind of thing, how do we do a homework assignment that requires file input output? So I'll go ahead and switch gear and talk about your next homework assignment due in 1 week. That one is in topic 6, and the homework assignment is called file IO. And it involves, a gzip, tar file, as usual. So we'll go ahead and save this link to fileio.tar.gz, and we'll put it into the temp folder. Okay. Switch to the temp folder using cd tar xzvf, that particular folder. That particular tar file, and change the directory to file IO. And all the instructions are inside file IO itself as an assembly language file. And just like your last homework assignment, it starts off, the only thing I give you is basically C code. Okay, this is actually regular C code. It is compilable if you have to write headers. This file is actually compilable. In fact, I can show you exactly how to do it. Okay.
Prove it.
Prove it, exactly. Okay, so what we want to do is to make a copy of this file first. So we'll call the new one fileio.c. This is a regular C file, it is not C++. And then the first thing we want to do is to get rid of the pound sign, because the pound sign is not really useful. It's a flag to let the CPP or the C preprocessor know, okay, there's something for you. So in this case, that's not the intention of this. So we'll go ahead and get rid of all the pound signs, and now we have almost a C program left. Right? So we want to do a pound include here, and to figure out what you have to do to what you have to pound include as a header file, you just say man to read, and it tells you uni std Unix standard .h file. So we'll go ahead and include that. UNISTD.h. And of course, in C, you have to wrap everything inside the main subroutine. So now we have main as a subroutine. Put it over here. And the rest should work for the most part. I'm going to let the C compiler check it. That's why we have a C compiler. Its job is to check all this stuff. Right? So gcc-o specify the output file name. If you want to run the C program inside GDB, you have to supply -g as an option. Okay, so -g as an option will include the symbolic information so it can associate an address to a particular line in the source code. So that makes it possible to use GDB to even debug your C and C++ programs. And then we specify the source file, which is file io.c. Okay, as expected, I forgot to do something here. I forgot to include a particular header file, and I can't even remember the name of that header file, but that's okay. That's why we have Google. So we just say, in32, in8, which header file, and differences. Okay, the name of the include file is stdint standard integer.h. So we'll go ahead and include that standard integer.h. And it doesn't work just like this. You have to have an underscore t. So, and this is underscore t as well. Exit. Compile. Aha! Now it works. Okay. Now that it works, the question is, how do I know whether this program is working or not? So let's go through this program written in C and find out what it does, and then we'll take a look at how do we test this program written in C to make sure that it does work the way it's supposed to. All right, so we'll go through this line by line. The obvious lines I'm not going to go through, but this one we will go through. Okay, what do you think this line does, based on what we talked about a little bit earlier? Okay, result is what we use to store the return value of calling read. Okay, and read is corresponding to system surface number 3. Okay, system surface number 3 means that you put EAX, you put 3 into EAX, and then the first parameter, which in this case is 0, specifies the file handle. File handle 0 is special because it is always open for any process. It is corresponding to standard in, or in C++ it is known as cin. Okay, so a file handle 0, or file descriptor 0, is corresponding to the standard input file of any process. The second parameter, which is stored in register ECX, is the address of CH. CH is my local variable here. That specifies where am I going to store the content that I'm reading back from the file. Are we doing okay so far? Okay. And then the last parameter, which is stored in EDX, is just a constant of 1 in this case. It specifies how many characters am I supposed to read with this operation. In other words, this one line is specifying, hey, operating system, I want to read 1 byte from standard in into the address of CH. And by the way, if you have any type of return code, store that into a local variable called result. Are we doing okay so far with the interpretation of this line? It's reading 1 byte from standard in into CH. And if there's any type of return value, you put it into result. Okay? In other words, it's the same thing as cin greater than ch semicolon in C++. Similar, not exactly the same, but close enough.
But it's stored to memory under switching CH. Or it's storing CH.
It's storing into CH, but since in C there's no way to pass anything by reference, you have to pass it by address. So the parameter itself is actually the address of CH, and that's what the ampersand is representing, is the address of CH.
It's stored in the register.
The address is specified in the register, but the byte is stored somewhere in memory.
Byte stored in memory.
Right. So the register acts kind of like a pointer. All right. So the second line, okay, so I'll just write here, read 1 byte from standard in into CH, and you'll store the result code into store the result code from the subroutine call into result as a variable. What kind of return code are we talking about? Well, if you read this man page, it tells you exactly what it is. return value. On success, the number of bytes read is returned. Okay, so let's go back to the program here. How many bytes am I requesting? 1. So that means if I am successful reading, it has to return a number of 1. That's right. Okay. Now, if you keep reading this one, and 0 indicates end of file. So if you request to read 1 byte, and it comes back and say nothing, 0, that means you're already at the end of file of whatever file you're trying to read. Is that okay so far? Okay. That is the only thing we have to do, because it's not. We can assume that it's not going to return -1. In other words, it's not going to be erroneous. Question?
I said we hope.
We hope, yes. All right. The next line is, the conditional statement. It's a huge conditional statement here, and the whole thing is inside the do-while loop. So what the conditional statement does is to say, if result, do the following. In other words, if result is non-zero, do the following. Okay? Because if result is 0, that means we are at the end of file. I did not read back anything. There's nothing to process. If result is non-zero, assuming there's not an error, it means I just read back 1 character. Let's do some processing here. So inside this outer conditional statement is some inner conditional statements, and the inner conditional statement is they look kind of cryptic, but all they really mean is to say, in this case, in this particular branch, all it's saying is if the character that it was read is 0 to 9 or A to F in lowercase, do the following. Okay, is that making sense so far? If CH is greater than or equal to the ASCII code of 0, and CH is less than or equal to the ASCII code of 9, or CH is greater than or equal to the lowercase a ASCII code and less than the ASCII code of F, do the following. So we want to, let's see what it is going to do in this case. It's going to write the same byte to another file descriptor. So this is basically saying write 1 byte from CH to standard out in this case. The first one in the parameters is the file descriptor. File descriptor 1 is standard out, otherwise known as C out in C++ or STD out in C programming. The second parameter specifies what am I writing from. This is a memory location, and the last parameter specifies how many bytes am I writing from that location. In other words, it's kind of the reverse of read. Instead of writing, instead of reading, I'm writing. But the 3 parameters have about the same meaning. It's just the direction of transfer is different. Are we doing okay so far with this code here? Okay. The rest is really just regular code. The rest of the program is just saying, okay, if it is between A to Z uppercase or between A to Z in lowercase, write it to file descriptor 2. File descriptor 2 is also special. It is standard
block.
Standard std is file descriptor 2. It's file descriptor 2, and I'm not 100% sure about the file descriptor 3, whether there is a file descriptor 3 or not. I think it's standard log. So file descriptor 3 is standard log, and it is there. So I'm basically taking an input stream, and based on what I'm reading, I basically send it to different files as the output. Are there any questions about this program at this point? Yep.
The intersects.
They intersect, yes, they do. Okay, the first condition and the second condition intersect, which means A to F is is actually present in the first condition as well as the second condition. It's okay. Well, I'm pretty sure you guys know what the behavior of the program is supposed to be when you have lowercase a in red. It is a multi-branch conditional statement using the else if construct. So it means that it will only go to one destination. I'll leave it up to you guys to figure out which one it is supposed to output to. Because that's a C concept, it's not assembly language programming concept. Okay? But actually it's a pre-C concept, it's not even a C concept, it's a concept of conditional statements in general. All right, so this is a loop, this is a do-while loop, which means it's a poll checking loop. It will basically perform whatever is specified here, and then depending on the value of result, it will determine whether it wants to go back and do it all over again. Are there any questions about the logic of this code? How do we test it? Well, you can test it in some, in various ways. So I'm going to show you guys, how to test this program. Whatever you do, don't do this. Okay? Just running the program by itself without anything is not going to be very helpful. Okay? I'll show you exactly why I say that. Okay? This is not very helpful. Okay? This is what I type on the keyboard. Press the Enter key, and it stripped out all the spaces and all the punctuations, and that's it. Okay? That's because where do you think the punctuations or the space bar went? File descriptor 3.
Yeah.
3. File descriptor 3, and file descriptor 3 is sending it to the log file. And how do we stop this? How do we stop?
Control C.
Control C can stop, but it's going to interrupt the flow of the logic. So the proper way to
You
stop
need
this
a-
is Control D,
In the file.
end of file, right? Control D will stop the program. Because in Linux, Control D, when you're dealing with static in, is the indication of end of file. So when you're done with the file, you just use Control D and you're done. All right? But this is not really helpful because it doesn't tell me, because remember the code, the lowercase e is supposed to go to one file, and then all of the other letters should go to another file. But it's not shown here because without any type of redirect, standard out and standard are both going to the console. So that's why we cannot differentiate, which one is going where. So to test a program like this, the best way to do it is to create a test file first. Okay, so we'll go ahead and create a test file. A test file, simply means that you have to give it something like 1, 2, 3, ABC on one line, because that should go to one particular place. And then you have something else like uppercase ABC and then lowercase ABC to see what happens to this line. And then we have XYZ and let's say some punctuations over here. Okay. So that's my test file. Okay, these are 3 lines that I'm supposed to be testing, and we'll go ahead and write this file as test.txt as a text file. All right. And now I can use redirect to redirect the input file from that text file instead of typing something on the keyboard. So now I can run the program file IO with a redirection symbol, which is the less than symbol, and say, I want to use the file content of test.txt as the test file. Okay, that's not very helpful either. That's because the output is not redirected. Everything is still going to the console, and they're all jumbled up. Okay, great. What do we do with this program to test it? Because I really need to know where ABC 1, 2, 3 ABC lowercase is going, where ABC uppercase is going, the line feed characters, the space, all the punctuations. I need to know where they're going. Okay, let's try this again. But this time we'll use another type of redirection, which is redirecting the output of the program to specific files. Okay, 1 greater than means file descriptor 1 goes to this file. So we'll say test1.log or test.1.log. I mean, however you want to name the files is okay. 2 greater than to test.2.log. So these are output files. It will overwrite these files, so you have to be sure that these files are okay to be overwritten. Test.3.log, and nothing happened. What? Let's do it again. Press the Enter key. Nothing happened. What?
Yeah.
Because all of the output are now redirected to the output files, so the console is not showing anything anymore. Is that making any sense? Because normally the output is going to the console without the redirection, and that's why we see output from the program. But now that I'm redirecting the output to specific files, there's nothing specified to output to the console anymore. So the console doesn't do a single thing; it doesn't see a single thing. Great. So how do we know whether this program is now working or not? Well, we can do something like this. We can say, let's take a look at all of the log files. And with VI, you can actually specify the wildcard like that, and then it will open one file next to the other one. You can also specify options like -O, lowercase or uppercase. Then you can open all files at once, using different tabs, quote-unquote tabs. Not tabs, but they're open concurrently. And I cannot remember which one is horizontal and which one is vertical, but okay, lowercase is horizontal, or splitting vertically. So now we can open all three files at the same time, and you can see that whatever we redirect to, whatever is using file descriptor 1 is 123 lowercase abc, lowercase abc. Does that match the logic of the program? What about everything that is A to Z, uppercase or lowercase, other than lowercase 1 to 8, lowercase a to f? They're all going to file descriptor 2. Does that match what the program is supposed to do? What about everything else? The punctuations, the space, the line feed character, and that's why you see the empty lines. They're all going to file descriptor 3. Okay? So that's how we can test the program and go like, oh, okay, so this is what the program is supposed to do. Okay, so the C code is specifying the logic to do this. Now you have to implement this program in assembly and give me exactly the same output, assuming the input is what we just fed this program. Are there any questions at this point about what the program is supposed to do and how to test the program? The method to test the program is independent to the programming language itself. Okay? Right. Now, when I'm done doing something like this, I probably want to, basically, create a test case. So I have one test case, based on these 4 files, one serving as the input and the 3, specifying the output. And I'm not going to overwrite these files. I'm going to archive these files and make sure that they're safe somewhere. Because when you test your program using test.txt, you need to test the output of your program written in assembly against the expected output, which is test1.log, test2.log, and test3.log. Okay? How do we compare files? I don't really want to use VI and visually go through the lines because you can miss something. Like the null character, which is ASCII code 0, is not shown in an editor. Okay? So how do you compare 2 files and make sure they're the same? Let me change the command line a little bit, and let's just say that this file IO executable is your program. So I want to generate the output to test A.1, test A.2, and test A.3. So I'm outputting into 3 different files in this case. All right. So at this point, I want to check to see whether the program is matching the output, whether the output files are matching or not. So how do you compare 2 files? There are several utilities.
Linux command.
Linux command to do it. There are several commands to do it. The first one is called diff. So now you can say diff test a.1.log, and you can test it against test1.log, which is the correct output of the file of this program. And if it does not report any differences, it checks out. Okay, these 2 files are the same. And you can do the same thing with the second file, which is capturing the output to file descriptor 2, checks out, and the one to file descriptor 3 checks out. So at this point, I'm sure that this program is working consistently because it is the same program to begin with. But in your case, you'll be using your own code and test it against the other one. Are we doing okay so far? Yep. Sorry? Diff will tell you how they're different if they're not the same. Okay, so let's go ahead and mess it up. Okay, let's mess it up a little bit. Okay, so let's go ahead and I'm going to copy the file name first, so I save one version of the good one. Okay. So we'll go ahead and mess up this program, and let's just say that in the implementation of this, for whatever reason, instead of using else if, I just say if. Okay. Now, this is really tricky because without that else, syntactically it is still correct, but now it means something that is different. Okay, let's go ahead and test this one and see how it is different. Okay, and we have to first make sure that it does compile. Exclamation point GCC means repeat the previous command that started with GCC as the first part of the command. So it's a pretty nifty trick, because it just saves you a lot of time. And now we can run the program again. I'm just using the up arrow key to find the command that I used, which is this one. Okay, so now I have a messed up file I/O program generating potentially files that are different from what they are supposed to be. So I would run the program. Doesn't give me anything, but the diff commands will tell me something, hopefully. So the first one is looking at whatever is supposed to go to file descriptor 1. Do you think there should be any differences here? No. This one should not have any differences because the first condition is the first condition. Okay, that part has not changed. So you look at this and go, okay, diff did not detect any differences. It's good. Look at the second file. What do you think about the second file? It's different. Okay, so diff gives you a human readable change to tell you that one line has changed, line 1 has changed. It was, in test a.2.log, it's lowercase abc, uppercase abc, lowercase abc, and then xyz. And then in the other file, it is abc uppercase and then xyz. Okay. So not only does it tell you that there is a difference, it tells you how they are different. All the other lines are identical, so they are not mentioned here. It has a little warning saying that no new line at the end of file, which is unusual for a file, but that's okay. It's not really a problem in this case. Are we still doing okay so far with how to test your program? Okay, all right. So what you need to do is to do something like this when you are testing the program. But how do I test the program, generating the output file and using GDB at the same time? Okay, so that's something that we also have to talk about. So we want to use GDB file IO in this case. So we're going to run we're going to run file IO inside GDB in this case. So we can use the debugger to help us figure out, okay, what is wrong with this program now? Okay, all the usual things will still work. L for list. And I suspect, the problem starts on line 20. Okay, so I'm going to put a breakpoint on line 20. You can do the same thing in your assembly code. Just use your B whatever line number to specify breakpoints. So everything that you have learned up to this point will still work with this program. What is new to this particular program is when you run the program, you can also use redirection. So in this case, I can use exactly the same thing, with the command line when I ran the program by hand. So I can say redirect the input from test.txt, redirect the first file descriptor to, I'm just going to be lazy and just say it's 1.log, the second descriptor to 2.log, and then the third file descriptor 3 to 3.log. Okay, you can actually do that. Press the enter key, and now the program is running, and it's now at the breakpoint of line 20. So everything that you know about debugging a program still works, even with all the redirection. It's just that when you run the program using the R command, you have to specify the redirections as well. Then it will work basically the same way. As this program is running in GDB, you are probably curious, okay, what is the content in 1.log at this point? What is the content of 2.log at this point? It's difficult to do it inside GDB. You can shell out to look at the content of a file, but it's difficult. So the other thing you can do, assuming you have multiple ways, or a way to open up multiple terminals, is to open up a new terminal and do an ls. And in this terminal, you can use VI, you can use nano, you can use cat, you can use less. Of all of these things, are ways to look into a file. So I can, in this case, I can just use cat and look at 1.log, and it is empty at this point. No, excuse me, it's not empty. It has a character of 1. Because there's a lack of line feed character, that's why it is on the same line as the prompt itself. Okay. If you think that this may not be the best way, because if I have any hidden characters like control, like the null character, which will not show up here, the other way to do this is to use hex dump, or basically a program that can dump out the content in hexadecimal. So you can now use hex dump to look at the content of the file, and I think -c looks at each one as a character. So I can look at 1.log as a dump. So in this case, it is just printing out the character itself. So if you use man hex dump, it will show you all the options they can do. So 1 byte in octal, 1 byte character display, canonical hex plus ASCII. That's probably what we want. Okay, dash uppercase C. So we'll go ahead and use dash uppercase C. So this is the output. It shows you that the first byte, the only byte in this case of this particular file, is 3131 in hexadecimal as ASCII code, and 1 as a printable character. Okay? And you can use this, on a variety of files. Okay. So let's go ahead and do a hex dump dash uppercase C on the actual, correct output for file descriptor 1. Okay. So that would be test.1.log in this case, and it shows you that it has these many files: 31, 32, 33. Those are ASCII code in hexadecimal, and on this side it shows you the actual representation of those particular characters. The one that is interesting is file descriptor 3, because file descriptor 3 is the one that captures everything that is not A to Z, lowercase, uppercase, or 0 to 9 as digits. So that would include the line feed characters, and all the weird stuff, right? So let's take a look at the hex dump of that particular file and see what it looks like. Okay, so in the ASCII code, you have 0A, which is the line feed character, 0A, which is the line feed character, 21 is the exclamation point, 40 is the @ symbol, 23 is the pound sign, 24 is the $sign, and then the 0A here is a dot because it's not a printable character. Okay. So this way, not only do you know exactly how many bytes are in the file, including the non-printable characters, you also know the exact ASCII code of those particular characters. Are we doing okay so far with the tools that you need in order to debug your program? So there are a few new tools that you need to use for this particular homework assignment, but those are useful tools to begin with. When you are using Linux or any type of programming environment, these are all useful tools to have. Any questions at this point? No questions? Okay, if there are no questions at this point, then I'm going to show you a test program that will show you how to do the translation. Okay, so let's go ahead and switch gear to a different folder. Okay, I'm going to use a separate folder of test.io. Okay, instead of file.io, we have test.io here, and I'm going to give myself a quote-unquote mini homework assignment so that I can go through the process of doing the translation that you will need to do in order to do your homework assignment. And on top of that, I will also show you what you need to do, or where in my notes you can find the instruction that you need in order to do the homework assignment. So we go back to my notes here. So what you need to do is to go to OS calls, operating system calls in assembly language, and that is my own notes. And it gives you, all the information that you need in order to read a file in Linux and also to write to a file in Linux. Okay, so we'll click on this one. It gives you instructions, sample code, and how to test it in GDB. In other words, this actually overlaps quite a bit with what we talked about earlier in today's class for reading a file, and then we can have another one to talk about how to write to a file. This one, talks about how to write to a file, and it just talks about the same stuff that we talked about a little bit earlier. Are there any questions at this point before I move on and actually do it interactively, so that I can show you, what you need to do to read from a file and what you need to do to write to a file? Questions? Okay, so let's go ahead and do something, write a sample program to illustrate all of these things and hopefully tie everything together. So we'll say test input. Okay, so the only purpose of this program is to test how do we read something in from a file, from file descriptor 0, which is standard in. Okay. So we'll have dot data here because I need to allocate a buffer. So I'm gonna say buffer and dot byte. Well, I can use dot byte or dot fill, which is more handy. So with dot fill, it is the same thing as allocating 20 bytes in this case, and all the bytes are zeros. So it's the same thing as dot byte, 0, comma 0, comma 0, comma 0, fill it up with 20 zeros. Okay? This is a shorthand. It's handy. It's just easier to use in this case. Dot text, dot global underscore start. All the usual stuff that we have to do. Underscore start, and we're not going to waste any time. We'll move 3 into EAX. We'll move. That is specifying this is a read operation. The first parameter goes to EBX, and that specifies the file descriptor. File descriptor 0 is standard in. We put that into EBX. The second parameter is going into ECX. It specifies the location where we are going to read the content into. So we will be reading from the file and stash it into this content here. In this case, we need to specify the address of the buffer, and we put that into ECX. And then the last parameter specifies how many bytes do I want to read. So in this case, let's specify 20 because I have a buffer that can, handle up to 20 characters. So we put that into EDX. After we set up all the registers, the trigger to request an operating system service is to do an int, which stands for software interrupt. It's not integer, it is interrupt. $, which means it's an immediate operand 0x80 because that's the vector where we want to trigger the software interrupt. Okay. That's it. This is my entire program. After this, I'm going to do the usual exit code. But now the usual exit code starts to make sense, hopefully, because what does it look like to you? This is my usual exit code, the last 3 lines. It's exit 0, right? Because the 1 that we put into EAX specifies we want to exit. We're telling the operating system this process wants to exit. The 0 that we put into EBX specifies the exit code itself. So it's the same thing as in C, exit open paren, 0 close paren. Okay, so now it starts to make sense. Why are we adding every single program with these 3 lines of code? Because we want to exit the program properly by returning a code of 0. In Linux, and I suspect in all Unix type operating systems, an exit code of 0 means everything is good. Okay, there's no problem. All right, so now that we have this program all written, let's go ahead and do something about it. With any program that involves reading from standard in, it is not a good idea to run it with user interaction. So I'm going to use a test input file just like before, except in this case, my input file is going to have A, B, C, and D, E, F only. Okay, so I have 2 lines of text here. So the question, okay, before I exit the editor, let me ask you guys, how many bytes are in this file?
8.
There are 8. That is correct. Because ABC is followed by
A new line.
the line V character, which is a new line character. 10 is the ASCII code. And then DEF is the second line. It's also ended with its own end of line character, which is another line V character. So when you dump this out using text dump dash uppercase C, it will be the ASCII code of ABC, and then 0A, which is the ASCII code of the line V character in hexadecimal, DEF, the ASCII code, and then another 0A after that, which is the line V character, the last one. Okay. Great. Hold on. I asked the
20,
system to read 20 bytes, but the entire file only has 8. So what is going to happen?
Wait.
Well,
Wait.
we'll see. Okay, we'll see what happens. Okay. In fact, I'm going to change my program just one more time. Okay, I'm going to do a copy and paste here. So 6 lines copied and pasted over here. So I'm going to repeat this operation twice. I'm going to attempt to read 20 bytes twice from standard in. But that's going to be bad because the file only has 8 characters. I don't even have enough characters to feed the first call to read. What about the second one? Well, let's find out what's going to happen here. Okay. All right, so we'll do a assemble test input.o, test input.s, link it to test input. and then we'll GDB the program. All right. Take a look at the program first, and then say, well, do we want to set up some breakpoints? Absolutely, we want to set up some breakpoints. There's really nothing interesting on line 7 to line 12 because we can set up a breakpoint over there, but we already know what those lines are going to do. We're just going to put something into the registers EAX to EDX, and then we call the system and say, hey, operating system, I need you to do something. So none of those lines really have anything interesting to report. The first line that has something interesting to report is line 14, because it's right after the system performs its operation. Okay, so we want to put a breakpoint on line 14, okay, and then run the program. And this time we want to make sure that we run the program with redirection so that I don't have to type the input interactively, because that's going to interfere with GDB's own input, and I don't want to do that. Okay. So now we are done with the first call to the system, and the first thing we want to check is the buffer itself. Okay, what is actually in the buffer at this point? So we want to do an examine, and we want to examine all 20 locations, each one treated as a byte. And well, if you want to, you can print those things as characters. BC means that it is going to be printed as characters if it is possible. If not, it will print it out as the actual ASCII code. And we want to do it, with buffer. Okay. All right. Does that make sense to you? The first byte has an ASCII code of 97 in decimal, and it has the actual code of A, and then we have ABC. The fourth one is 10 in decimal, and it is represented as \n, which is the line feed character. And then we have DF, another line feed character. Okay, it seems to make sense. Okay,
Yeah.
but what about the return value of read? It goes into EAX. Okay, so the return value of read and the return value of write is actually the value of EAX after int $0x80 comes back to your program. So we want to do a IREAX or print $EAX, whichever one you want to use is fine, and say, oh, the read operation returns a value of 8. Is that consistent with the man page on read about the return value? What is the return value of read according to the man page? The number of characters actually read. Okay, exactly. And does that make sense to you? Sure. My file only has 8 characters to begin with. Okay, that's okay. Okay, and we read all 8 characters into buffer. Good. Now we would do the second attempt to read from the same file. But we remember we are already at the end of file because I have read everything there is to read from that file. Okay, what do you think should happen this time? And I want to put a breakpoint on line 21 because that's right after the second int $0x80. And then you'll continue to run the program. Continue is C. And now we are stopping, after the second int. Okay, first of all, let's go ahead and re-examine what is in buffer. What do you think should be in buffer at this point?
It's the same.
It should be the same, exactly. But why should it be the same? There's nothing to read. That should clear out everything in buffer. Nope, because if you have nothing to read, then you're not going to overwrite anything in buffer. Okay? It only overwrites whatever is reading from the file. And since we're already at the end of file before the second attempt to read, there's nothing read back at this point. But how do I know that is the case? How do I know that there's nothing read this time? Which register reflects the number of characters actually read? EAX. Okay, so we want to take a look at EAX, and what do you expect in EAX at this point? 0. That's right. Well, first of all, we'll run this command here and make sure the buffer still has ABC, line feed, DEF, line feed. Okay, that's good. And then we look at EAX, and EAX is 0. The operating system is coming back and say that, well, we are already at the end of file. There's nothing to read. And that's why I read 0 characters. It's not erroneous. It is not a problem. It's just that, hey, there's nothing for me to read at this point. Are we doing okay so far with this sample program? Okay. Can you guys see how this program relates to your homework assignment? Okay, very good. So we will go, no? It will connect. It will connect. Now let's go ahead and reverse this and talk about how to write something to a file. So we'll go ahead and write a second program called test output, because that's all this program is going to do, is to specify some output. And with test output, I don't need dot data anymore because I don't need to overwrite anything. Everything can go into dot text here. Dot global underscore start. And the way I'm going to do this is I'm going to do it in the lazy way. And I'll have output string as a label definition here. And this time I'm going to use ASCII, .ASCII, so that I don't have to spell out every single ASCII code of what I want to print. Okay. So in this case, I'm going to say, oh, this is another sample program.
You use single quotes instead of double here?
Yeah, I use single quote here.
Okay.
I think the syntax is single quote. I'm not sure. I'll let the assembler decide.
I was just wondering if you could increase the font size.
Oh, increase the font size.
Sure.
Terminal. Under view. Edit. Preferences. There we go. Better?
Yeah.
Okay. All right. And just to make it look nice, I'm going to have I'll have the line feed character after this. A line feed character is nothing more than a byte that has a value of 10 in decimal or 0.8 in hexadecimal. Same thing. Okay. All right. And on top of this, I'm going to say output string end is a label. Okay? Because I need to calculate the number of bytes to output. So this is basically it will help me calculate the number of bytes to output. For those of you who don't like to do calculations when you're actually using it, you can do something like this. You can say output string length is output string end, which is basically just a number, minus output string, which is another number. That's perfectly okay. In other words, you can say how many bytes are between these two labels. That's basically what it's saying. Okay, which turns out to be the number of bytes that we want to output in this case. So that's a handy label to define, in this case. Okay, this is the starting point of the entire program, and we'll go ahead and just, request system surface number 4, which is writing to a file, and that has to be put into EAX to specify what operation we are requesting. We put $1 in this case into EBX because that's file descriptor 1, which corresponds to standard out in this case. And we'll put the address of the first byte that we want to output into ECX. In this case, it is the label output string. Put it into ECX. And then last, we want to specify the number of bytes we want to output to standard out into EDX. And in this case, it is the label called output string length, and put that into EDX. And don't forget the actual important part, which is to output, to actually do the request, because if you forget about this particular instruction, nothing's going to happen. Okay. And then after that, we have the usual exit code, which is move 1 into EAX, and then move 0 into EBX, and do the int to request. We are ready to go. We are ready to exit with a code of 0. Are there any questions about the assembly code itself in this case? This is pretty much the same stuff in my notes. Okay, I'm just doing this more interactively so I can show you exactly how to run the program and how to test the program. Question?
Is there a redirect? Is there a way to hard code output file or no?
You cannot specify the name of the output file, but what you can do is to use the open call, the open system call. That is how you can open a file based on its file name and the path. And it returns an integer, which is the file descriptor. So you can save that file descriptor to a location, and then from that point on, if you want to output to the file that you just named, you can output to that file descriptor. So if you want to control which file you're dealing with from inside the program without using redirection, you will need to use system service number 5 for open and number 6 for close. So you will need to use those particular system calls. But I'm focusing on just standard in and standard out, so I'm not bothering to open and close files. All right, so let's go ahead and test this program. Assemble. Junk at end of line, unrecognized character is 8, and that's on line 4. On line 4, it's this one. Okay, so maybe it's double quotes. All right, that's it. LD test output, and the input to the linker is test output.o. And once again, we can use GDB to test the program. List the program, take a look. I want to put a breakpoint on line 18. In other words, I want to look at the return value from the system call and see if it makes any sense. And when we run this program, once again, we can redirect the output from inside GDB, which is really handy because this way the output of GDB will not be interfered by the output of the program itself. Okay, which is the way I like it, because I don't like the output of my own program to be intermingled with the output of GDB itself. Okay, so I can just run it with a redirection to test.out. I'm just gonna name the file as test.log, whatever you want, doesn't matter. Okay, now we're at a breakpoint. In a separate window or separate prompt, I can now take a look at. Okay, this is in the wrong folder. At this we can take a look at the output, which is test.log. So we can now say, okay, what is in test.log? I can use VI or nano, but it's better to use hex dump because this way I won't miss anything. Okay, even non-printable characters will be shown here. This is the content of test.log as a file. What you see on the left, all the way to the left would be the locations. So each line has 16 bytes. So the location itself is specified in hexadecimal. Let me just highlight which part we're talking about here. This is all in hexadecimal. So the next line is starting at location 16 of the actual output or the file location in the file. These are ASCII codes, but they're ASCII codes in hexadecimal. And then these are the actual printable characters. When it's printable, it will show as it is printable. If it is not printable, like the 0A here, it is represented by a single dot, which basically says, okay, there's something here, but it's non-printable. Do we have any questions about the output of the test program? Is that what it's supposed to be? Okay, that's what it's supposed to output. And we can now switch back to GDB and say, oh, not this one, the other GDB here. Because I want to check the output or the return value of this write operation. What do you think it should be returning in this case? How many characters got output, okay? And to quickly figure out how many characters is already in the file, we can use another tool here, which is ls-l. We can use ls-l to look at test.log, and it tells me that it has 31 characters. This 31 here is reflecting the size of the file, and it should be 31. So when we go back to the test program inside GDB, the value of EAX, which is the return value of the write operation, should be 31 in decimal, because that's the number of characters that we write to standard out in the previous system request. Is that part making any sense? Okay, so let's go ahead and take a look at EAX, and it is 31. Okay. Yep.
Is that why the last line was stopping at 31 after 16? It was 1 0 and
It's 1F.
Yeah.
Yeah, 1F is 31.
Yeah, that's why it was stopping there.
Correct. But it seems to be off by 1 because the offset starts from location 0. Okay. Let me re-explain it, because some people might have missed it when we display this one. So you can see that the first byte is at offset 0 from the beginning of the file. So when we go to location 1F, it is already past the end of the file. But location 1F is actually what we normally call byte 32 because we are counting from 0. So the file actually only has 31 characters or 31 bytes because the indexing starts from 0 in this case. So the most reliable way to find out what is the size of the file is really just say ls-l and then the name of the file and use that to tell you how many bytes we have in the file. There was a question?
So that's why there's one missing byte at the end of that program.
That is correct.
That's that.
Yep, because that's exactly why there's an empty space here, and also why the vertical bar is shifted to the left-hand side, because that really is the extent of the file.
So if you had one more character in there, 1F would be 20?
Yeah, down here it will be 20, and then whatever is the ASCII code will go here.
Yeah.
Yep. And you can play with hex dump on multiple things. You can do a hex dump on the source code of the program if you want to. I mean, in this case, test output.cs is a text file, and that's what it looks like. Makes kind of perfect sense, right? You can also use it to look at the executable itself. It doesn't make a whole lot of sense to you because most of these are opcodes to the processor. So it doesn't make a whole lot of sense to us, except for there are certain things here that we can still recognize, right? This is another sample program. It is actually a part of the program, right? Because that's the text that we specified. What about this stuff down here? Test output.s, symtab, and I think underscore start is down here as well. So what about these guys? These are symbols, that we used in this particular program. And since we specified dash G steps or dash G steps, the symbol table is also included in this case, and that's why we can see all the label definitions or the name of the labels also in the executable file. Because otherwise, GDB would have no idea of what is upper string length. It would have no idea. But we store all of those things here as well as a part of the executable. So hex dump is pretty useful. It can be used to examine the content of the file without having the potential issue of what if something is not printable, because it prints everything in ASCII code and also hexadecimal. It's a tool very useful to hackers.
Yeah. They can change that. Can change.
No, you cannot change, but in order to make changes to a file, I'm not sure. I don't have it installed. There's a hex edit file.
You know what?
You can have a
what
hex
part of the file can change.
Yeah, there's a program called hex edit, if I remember correctly. -k hex, and we're going to find out whether that command is installed. These are all dumping utilities. There's no editor. I did not install it in my live ISO. But there is a program that allows you to edit the content of any file using hexadecimal values.
You can
So
you can change your
You
string.
can change the number of lives in the game to
and
200
your
instead
string.
of 5.
Your string is like instead of this is something.
Sorry?
You can your string.
Just
The content of the string. This is.
You can change it.
Yeah.
you cannot change it using hex dump.
No, but
You can make your own program to change it. You can just move to a certain offset and write a byte, and then you can change it that way too. Right. So are there any questions about this homework assignment? Questions? Okay, go ahead. That part is up to you. Okay, I'm giving you the tools. Whether you use my tools or whether you have better tools to use is entirely up to you. So I'm giving you a set of Harbor Freight tools. If you say, well, I got a default, okay, I don't care about Harbor Freight, use your own tools. If you say, I don't have any tools by myself, and you give me Harbor Freight tools, I use Harbor Freight tools, that's good with me too. But I don't think the tools that I give you are necessarily Harbor Freight quality. I think they're reasonable quality, like Bosch. But if you have Makita, you can use Makita if you want.
Are you gonna run the script on the assembly code?
Hmm?
Are you gonna run a script like you did on
Yep, yep, that's all gonna be script based. You know, I give you test cases and then I compare the output files to see
Are
whether
you
they're
giving
the
us
same.
the script that you're gonna be running?
In this case, I don't need to use GDB. GDB is strictly for debugging purposes because I can run the programs using the command line, capture the output, and compare the output to what they are expected to be. So you can do the same thing. So the first thing you guys want to do, you know, is really to change the programs into the C code, and you know, use the C code to generate test cases for yourselves. Okay, so you can say, okay, this looks like a tricky one. You know, generate the test case for the tricky one, and you know, give yourself like 1 or 2 at least, you know, test cases. And then when you write your program, you can test your program against the test cases already established by the C version of the same program. Question? Are there any questions about this? Yep.
I can understand how to end a file when you read from the keyboard.
Okay. When you're reading from the keyboard, you have a problem.
Yeah.
Because if you do a Control D, it depends on who is reading at the time. Because if you use GDB and you're using it in interactive mode, then sometimes, you know, whatever you type goes to the program that you are debugging, and other times, you know, it goes to GDB itself. So you have to be careful now, you know, when you type Control D, because if you type Control D at the wrong time, you can get out of GDB itself because it is end of file to GDB itself.
Can you show one more time? Reading from
A file?
Yeah.
Sure. Okay. So this is a demonstration of how to use GDB, you know, reading from a file.
No, not without GDB, just
Without GDB?
Yeah.
Oh, okay. Without GDB, just, you know, type the name of the
so
program.
you have 20 like characters, but you just enter 3 characters.
Uh-huh.
And how you know it's like end of your
Okay. Okay, the question is, you know, if you want to use GDB to debug the program, and you run it without using redirection, right?
Yeah.
Okay, you run it without redirection. So this is what happens when you run the program without redirection in GDB. It seems like the program is, you know, going into an infinite loop, but it's not, because it's really just prompting you and say, type something. I'm reading from static in. Okay. So what you can do at this point is actually to type something. Now, if I type ABC here and press the Enter key, nothing happens. Okay. And actually, something happened already. I'm actually running the second read at this point because I did not set up any breakpoints. So that's why the program is just proceeding to the second read. And this program is not going to give me anything as the output because, you know, I can type ABC again, and then if I press the Enter key one more time, it's going to exit because this is going to finish the second read operation. So to test what you want to test, we have to put a breakpoint on line 14.
So exit key is like end of file. Yeah?
Control D is end of file. So what we want to do is to run the program again, you know, type in ABC, and as soon as you press the Enter key, it will, you know, get out of the input mode. Okay. The problem with this one is, even though I have not specified Control D, it is still getting out of the system call, because when you run the program using interactive mode, it is what we call cooked. Okay, the cooked mode instead of the raw mode. In cooked mode, the line feed character is special. It will basically, you know, say, oh, okay, this is one chunk that your program may be interested in, and it will just stop there. Instead of reading all 8 characters at once, it will just stop reading the first 4 because it's a line feed character. So that's why, you know, I suggest to run this program or debug this program using redirection, so that you're feeding the entire program or feeding the entire test input to your program without any type of interaction when you're debugging the program. Yep.
So when you get to lines 12 and 19, that's when it does the redirect.
12 and 13.
The int command, the copy.
The int command is the one that triggers the operation.
That's triggering the input.
That's triggering the operating system to read something. Correct.
And that's waiting for the user.
Correct. Yep. So, you know, you can single step through line 7, 8, 9, 10 without anything. They're just
It's
regular
just moving,
instructions.
yeah.
Exactly. So by the time you get to line 12, and you say single step, it will give you, you know, nothing. and it's waiting for you to type something if you do not run it in redirection mode. So for all practical purposes, to debug this program, I suggest that you run that you use the redirection symbol because it's just easier to handle the program that way. All right. Any other questions related to this homework assignment? Yep. 20 points. So as I said, the point values of the homework assignments will continue to go up because the complexity kind of goes up, and then it involves different concepts. So later on, if we actually get a chance to run a binary search tree in assembly, that one's going to worth a lot of points because it would use recursion, it would use pointers, it would use structures, and all the things that you already know in C and C++. And believe me, by that time, it's not going to look that difficult. At this time, it looks like, whoa, are we really going to do all that stuff? Well, the answer is yes, but by that time, we would have understood enough stuff to construct programs in a way that it's not going to be that difficult. All right, so I'll see you guys on Thursday, unless you go to the lab to work on your homework assignment. Did you find the make calls? Okay, let me see if I can find it.
Yes.
So the whole homework assignment